Okay, so we're in section 6.4 now, and we're still looking at applications of the integral. And this one is going to feel a little bit different than the previous three sections that we've covered. Those sections, I think, are a little bit more geometric in nature. So we're talking about areas between curves and volumes of solids of revolution and things like that. This section deals more with physics. And what we're talking about here is specifically the concept of work, which you may be familiar with if you've taken a course in physics or physical sciences or what have you. But we're going to operate under the assumption that you're not familiar with it and introduce the concept just on the most basic level first. So in physics, what we're dealing a lot with are forces, and there's all sorts of different forces you could talk about. There's mechanical force, there's gravitational force, there's magnetic force, electric force, all sorts of different things. But a force in physics is something that has the potential to induce motion in an object. So a simple example is if I was pushing a shopping cart, for example. By me pushing the shopping cart, I'm applying a force to it, and that force, if I'm pushing hard enough and the wheels are not all messed up, should move the cart, should move that shopping cart. So a force will induce motion in a physical object. In physics, one of the first things we talk about when it comes to forces is what we refer to as Newton's second law of motion, which you are probably familiar with, but if not, this is it right here. So the force that I'm referring to, I'm going to notate with a capital F. All physical objects, all matter has mass. We're going to use a lowercase m to denote the mass of an object on which a force is being applied. And then A will represent the acceleration of that object that the force is inducing. Newton's second law of motion says that F equals ma, or in other words, the force is equal to the mass of the object times the acceleration of that object. Okay? Now, because this is Calculus 2 and you've already been through Calculus 1, we can be a little bit more specific with this little formula here. If we recall that the acceleration function is the second derivative of a position function, or a little bit more specifically, if you have an object that's being moved in a straight line relative to some starting point, and if we let s of t represent the position on that line of your object at whatever time t is, then the acceleration of that object is the second derivative of this function here. So we can replace that a with a second derivative of s with respect to t, and this is another way of representing this same principle, this same physical law. Okay? So with that said, that's specifically the topic of forces that we're talking about. In physics, where we get this idea of work, or the concept of work, is when we want to quantify the amount of effort, we can say, that a force puts into moving an object a certain distance. Okay, so we're taking the force that we're talking about here and also taking into consideration how far or what the distance is that the object is moved by that force, and however far that goes, it impacts the amount of work done by the force on that object. So we define work this way. This is a definition, not a physical law, but a definition. We say that the work done on an object by a force is equal to that force times the distance that the object is moved. Okay? So in other words, this work can increase if we apply a greater force on the object, or if we maintain that same force and just move it a further distance. Both of those things impact how large that work is. One really important note about this formula or this definition, this is assuming that the force being applied is constant. So again, if I'm pushing on a shopping cart and I'm moving it down, a grocery store aisle or something like that, I have to be maintaining a constant level of force on that shopping cart the entire time in order for this to be a valid formula. If my force changes, if I'm pushing harder at some points and not quite as hard at other points in time, then this formula needs to be adjusted. And that's kind of what we're going to do in this section. But again, we're starting from the most basic concept of work first. Before we get into an example, we have to talk about how we measure work. Specifically, what kind of units of measurement do we use? And to understand that, we're going to go back up here and look at the units of measurement that we talk about when we're referring to forces first. Now, there's two systems of measurement that come up when we're talking about things like this. There's the metric system, which is the system that most of the world uses to measure everything, including everyday quantities. And then there is the imperial system, which we're familiar with in America, but outside of America, it's very uncommonly used. So in the metric system, we talk about things like meters, kilograms, kilometers, and what have you. In the imperial system, we are dealing with things like feet and inches and pounds and that kind of stuff. Okay, so specifically for this section, the units you need to know, if we're operating in the metric system, we're going to measure mass in kilograms. Now you can swap that out for grams if that's more convenient for a problem, or some other denomination, but generally we're going to be dealing with kilograms. Distance is measured in meters specifically, okay? In both the metric and the imperial system, we measure time using the same units. We're going to use seconds for time, okay? So in the metric system, if we measure kilograms or mass in kilograms, meters for distance, time is measured in seconds, then acceleration in the metric system is always going to be given in terms of meters per second squared, okay? At least for our purposes. And again, that can be adjusted if it's more convenient to represent things in kilometers per minute squared or something like that. But for us, generally meters per second squared, that's what we're going to use. Now, from Newton's second law, remember this meters per second squared is acceleration, which we have here. But a force is mass times acceleration. So the units that we want to use for a force should be a unit of mass times a unit of acceleration. And again, mass in metric is measured in kilograms. So for the metric system, force is measured in kilograms times meters per second squared. Now that's, not only is that a lot to write, that's a lot to say as well. So we never actually referred to this unit as this. This kilogram times meter per second squared unit we define to be 1 Newton. So we're going to call this a Newton and use a capital N as our unit of measurement there. That's just simpler than saying this every time we need to use units of force. In the imperial system, things are a tad different. So in the imperial system, we have weight that we talk about. Usually in everyday language, we refer to the weight of objects more than we refer to their mass. So, you know, my 6-year-old, for example, he may weigh 45 pounds. I would normally say that instead of how many, units of mass he weighs. But the thing about weight is weight takes the acceleration due to gravity into account. If you've taken a physics class, you may have talked about this before. My mass here on Earth is the same as if I were on Mars. I would have the same mass in both locations, even though both locations have different gravitational forces applied to objects on their surface. But my weight would be different on each of those planets. My weight on Earth is going to be different than my weight on the surface of Mars. And that's because weight is a force. Weight is not the same thing as mass. My reason for going through all of that is because usually in a problem where we're doing work, we're kind of trying to compute work or a force or something like that, if your units are given to you in terms of the imperial system of units, you're typically going to be told the weight of an object, which we equate to the force due to gravity acting on that object, which means you won't need to find the force by doing mass times acceleration. The force will basically be given to you right away in those types of problems, okay? We'll see that because there's a lot of examples here that use imperial units. But then moving on to work, how do we compute the work done on an object by a force? Well, work, like we said before, is equal to force times the distance that the object is moved. And again, there's a difference between metric and imperial, how we measure this. So in the metric system, like we said, force is measured in newtons. Distance in the metric system is measured in meters. So that would mean that the work done is newtons times meters, or the units of work are newtons times meters, which we usually just call Newton meters, which you can see here. But once again, it's a little cumbersome to have two words to describe one unit, even though we do that for other things. In this case, we shortened this up by defining a Newton meter to be what's called a joule, and we use a capital J to abbreviate that. So 1 joule is a unit of work in the metric system, and it's the same thing as a Newton meter. If we're referring to units of work in the imperial system, the force would be measured in pounds, distance would be measured in feet, and so we call those foot-pounds, which sounds, I don't know, I think the first time I heard that, that sounded a little bit ridiculous, but that's what we call that, and we don't give it a shorter name like joules. It's literally just foot-pounds. This is the abbreviation for that. Okay, so now that we've gone through all of that preliminary stuff, let's try an example out. What I want to do is this part A, part B example here. So the first thing we're trying to work out, how much work is done in lifting a 7.5 kilogram toy from the ground to a table that is 1.4 meters high. And then we have this side note here, acceleration due to gravity, which we denote by a lowercase g, is 9.8 meters per second squared. If you've had any physical science class, any physics class, you probably know this one by heart because you've used it a gajillion times. Okay, so let's do this first, and then we'll read B and work through that second. We're computing work. We know that work is equal to force times distance. The force applied on an object times the distance the object is moved. And let's think about the force first. We're not told the force explicitly here because kilograms and meters per second squared, none of those are units of force in the metric system. And I know that I'm in the metric system because I'm seeing other units that are in the metric system. We're looking for something that would be measured in newtons, right? Which again, remember, newtons is the same thing as kilograms times meters per second squared, or a more helpful way to think of that is just to remember F equals m times a. I need to find the force that I have to apply on this object to lift it the distance given in that example, and that force will be equal to mass times some acceleration. Now, we're talking about the acceleration due to gravity here, and that's actually the acceleration that I want to use in that formula. The reason why is that because lifting an object straight up from the ground requires me to overcome the force due to gravity, then I'm applying I can think of that as applying a force that's equal to this, or that's going to counteract this force due to gravity by acting in the opposite direction. So if gravity acts downward, we would normally think of that as negative 9.8 meters per second squared. So acting in the opposite direction to lift an object straight up, I would think of that as a positive 9.8. So the force, which we're going to start with, is going to be equal to the mass times the acceleration that we're trying to induce, which is the acceleration due to gravity. We're overcoming that, mg. The mass of our object is 7.5 kilograms, and the acceleration due to gravity is 9.8 meters per second squared. Do that in a calculator or by hand, however you prefer. This comes out to 73.5, and remember the units here are newtons, okay? We haven't answered the question yet because we were asked for the work done by this force, so that's the next step. Work is equal to the force times the distance. I had to figure out the force first. So now that I've done that, force is 73.5 newtons. The distance is how far I've lifted this object. So the toy was lifted 1.4 meters high. I'm going to multiply by 1.4. And this one works out to 192 Oh, no, I'm sorry. I'm looking at the wrong thing. Not 192. That's going to be part B. It's 102.9, and the units here are joules. We're in the metric system. Units of work for metric is joules. Awesome. Part B, similar problem. This one says how much work is done lifting a 35-pound child from the ground to your shoulders, assuming your shoulders are 5 feet 6 inches from the ground. Okay, so this is where we need to pay attention to the system of units that we're using and exactly what those units are. So we're talking about pounds and feet and inches. These are all imperial units of measure. So in the imperial system, remember, pounds, that's a force. So we don't need to do this preliminary step that we did in part A where we had to figure out the force as a first step. The 35 is the force in this problem. We know that right away. So we actually get to do this in one step. The work is equal to 35 pounds of force times my distance. How high am I lifting this child from the ground? Well, it says 5 feet 6 inches. You need to be careful about this because I'm getting two different units of measure here, feet and inches. But how we defined things, work was defined as, our unit of work in imperial units is defined to be a foot-pound. That means all units of distance have to be thought of as feet in order to have the correct units here. So 5 feet 6 inches, I know that 6 inches is half of a pound. So 5 feet 6 inches can be thought of as 5.5 pounds or 5.5 pounds. This works out to the thing I started to write up here, which is 192.5. Remember to include your units, foot-pounds. Okay, that's part B. So both of these problems did not involve any calculus whatsoever. In fact, we're 17 minutes into this video and we haven't done any calculus at all. In fact, we didn't even do any algebra. We did some very straightforward arithmetic. So clearly this shouldn't be what this section is all about because this is a calculus class after all. What we need to do is talk about where the concept of work starts to concern the concept of integrals. And where that is, as we alluded to before, is when this force is not constant. Here in this example, I was opposing the force of gravity, which is a constant force at the surface of the Earth. And so I had to apply a constant force on these objects to lift them. But in general, for most applications in physics, it's way too restrictive to assume that that force is a constant. It can vary. And we need to figure out how to compute work in those sorts of cases. So let's talk through that right here. Okay. Now, because our formula for work, I'm just reading this part up here, assumes a constant acceleration, it's too restrictive for most real-world applications. So that's what we were just talking about. So let's assume that it's not. Let's assume that the force is varying at different positions as we move this object. Specifically, let's suppose that we have some object and we're moving it along the x-axis in the positive direction from x equals a to x equals b. And then let's suppose that f is given by a function. So capital F, meaning our force, is given by a function of x, where x corresponds to different positions on that x-axis. Okay, so depending on where we are on the x-axis, we might be applying different forces, and this function will give us that force as a function of our position. It's important to note here that we're going to be assuming that this is a continuous function. If it's not continuous, then we won't get to do what we're about to do here. But in practice, that's generally going to be the case anyways. Forces, for the most part, can be represented by continuous functions. So that's not a super unrealistic assumption to be making. Now what we're going to do is we're going to think of that interval, AB, that we're moving this object along on the x-axis. We're going to partition it up into subintervals, the way that we do when we define Riemann sums and the definite integral. Let's suppose that the endpoints for that each of these subintervals are x0, x1, x2, and so on until we get to xn. And let's suppose that we also chose these endpoints so that all of the subintervals have the exact same width, which we're going to be denoting by delta x. That's typical. This is familiar stuff for you. Then what we're going to do is for each one of those subintervals, xi minus 1, xi for a general one, we're going to pick a sample point, xi star. So some sample point that lives in that subinterval. Again, this is exactly what we do when we define the definite integral. Okay? So if I wanted to find the force being applied to the object at that exact sample point, that's what this function f of xi star represents. That's how we defined it, right? Now, think about this for a second. I'm going to draw a little piece of our x-axis here, specifically where the object in question here is being moved. So we're going to move an object from point A to point B. And what I've done is I've cut this up into a whole bunch of these little subintervals, right? So I'm going to think of that one there as xi minus 1, and this one is xi. And we've chosen some little sample point in there, xi star, right? Now, even though our function f varies, it's going to change for different values of x. If I choose this interval to be small enough, then I would expect f of x to not vary a whole lot within a teeny tiny little subinterval. And that's the reason why we have to assume f is continuous, because that's kind of the important property that continuous functions have. In other words, if a function is continuous, then small changes in your independent variable will induce relatively small changes in your output variable. So in other words, a small change in my distance here, or in my position, should only induce very, very small changes in the force applied throughout that interval. The reason that's important is because if all of the positions in this tiny little subinterval give me pretty similar forces when I plug them into that function, then I can just approximate the force done throughout this little subinterval by f of xi star. Because the actual force being applied at other points within that subinterval should not be very, very different from that, given how small we chose that subinterval, okay? The reason that matters is because if I choose to approximate all of the force applied throughout this subinterval by just a single quantity, f of xi star, then I'm approximating that force with a constant. And that's what allows me to go back to my original work formula where force was assumed to be constant, okay? So that's what we're saying right here. If delta x is small, meaning I have a small subinterval, then f of x will not vary much over that subinterval, and we can approximate the force applied across that subinterval by f of xi star. Because that's a constant, we can use our work formula and approximate the work done moving the object only across that subinterval, which I'm going to call wi, because it's the ith subinterval, by f of xi star, that would be the force that we're using as an approximation, times delta x, because delta x is the distance that it would move from here to here, if that's the width of that subinterval. Okay? Now, keeping in mind that I divided up my entire interval AB into all of these little subintervals, what I can do is compute the work done over each one using this approximation. Notice you'll get a different sample point for each one of those subintervals. And then I can add them all up, because that's a property of work. If you take the work done over a large interval, one way to compute that is to take the work done over all of these little pieces and then add them up. You would get the same thing as the total work. So that means the work done moving this object from point A to point B on the x-axis can be approximated by summing all of those wi's. That would look like this summation. As you would probably expect, that approximation is going to get better and better the smaller we can make these subintervals. But we can make these intervals smaller and smaller by letting n get larger and larger. So if we let n go to infinity, we should get the exact work done, moving this object from point A to point B. And as you know, if you take the limit as n goes to infinity of this type of a sum, this is a Riemann sum, that becomes an integral. And this is the result that we were looking for. The work done, moving an object from point A to point B, where the force acting on that object is given as f of x, as we described before, It can be computed by taking the definite integral from a to b. Notice this is the endpoints of the interval that we're moving our object along, of your force function, f of x dx. Okay? That's what we're going to be using for the remainder of this section to answer the questions that are coming. But this is a good point to stop this first part.